So, as you know, that additive manufacturing has capability of making very unique and complex parts like this artwork or this very uniquely designed metallic sculpture. But there are many current issues in additive manufacturing since this is an emerging process, and machine learning has the capability to solve many such problems. So in my talk, I am going to briefly introduce metal additive manufacturing processes and its several uniqueness and opportunities. And then through several examples, I will show you why we need machine learning. And then I will give several examples for several applications, and then several hands-on calculations to use machine learning for solving problems in additive manufacturing. And then I'm going to conclude with future perspective and impact of this particular area of study. So, as you know, that a metal additive manufacturing process is a layer by layer deposition process where we deposit thin layer of powders, often thinner than human hair, and we selectively melt those using heat source such as laser beam, electron beam, electric arc, and then when they solidify, they make part in 3D. So depending on which heat source you are using and in which form you are supplying the material, there are three main metal additive manufacturing processes. So the directed energy deposition process laser, here we use laser as the heat source and we supply material in the form of powder. In DDGMA process, we supply the feedstock in terms of wire and it's melted by electric arc. Compared to these two processes, in powder bed, we deposit thin layers of powders spreaded by a roller, and then that layers of powders are selectively melted by a laser beam as a heat source to make the material. Now, here I have a video uh, to show actually how laser powder bed fusion works. So first it deposits a thin layer of powder, and then a laser beam selectively scans to melt the material, and when it solidifies, it makes the product. The process continues after the entire part is printed in 3 dimensions. So there are many uniqueness of this process. Several years ago, in International Space Station, they needed a range, but that time NASA did not have any plan for supplying the essential commodities to International Space Station. So what they did, they sent a 3D design of the range from Houston, Texas to the International Space Station. And in the International Space Station, they had a 3D printer that actually printed the fully functional range. So even 20 years ago, it was a science fiction, but because of additive manufacturing, it is the reality now. At Penn State, we have shown that the dissimilar materials joint that are oftenly used in nuclear power plants, let's say dissimilar joint between a steel and a nickel alloy 800H, they are highly susceptible to creep failure at very high temperature. How to improve those joints? Replace those joints by introducing graded materials, where the composition gradually changes along the height of the joint. These kind of graded materials are much better in terms of improving the creep property at elevated temperature. At SVNIT Surat, also there are many fascinating applications of additive manufacturing in terms of making intricate and complex parts and prototypes that are also very fascinating. So you can appreciate that the revenue of this process is coming from various industries, starting from automotive, marine, aerospace, healthcare, so on and so forth. So you may ask, Tuhin, what is the problem then? Currently, among 5,000 alloys that we have, we can only print it a few. You can probably count in your two hands. And what is the issue? We still are unable to control structure, properties, and defects. So what do I mean by structure, properties, and defects? Let's say we print a part, a metallic part using additive manufacturing. When it solidifies, it forms a solidification structure. Now, in additive manufacturing, generally we observe two types of solidification structures, columnar and equiax. In columnar structure, the grains that form after solidification are very long, looks like columns. When you pull this part in the transverse direction, these grains have the tendency to separate from each other, and that forms cracks and also significantly degrades the tensile mechanical properties. In contrast, the smaller equiax grains are much better because you need to apply a high amount of stress to separate them. So our desire should be to transform the solidification morphology from columnar to equiax. That is the control of structure. Now, in additively manufactured part, the mechanical properties, for example hardness, vary significantly depending on where you are measuring it. So this spatial inhomogeneity of mechanical properties can affect serviceability and reliability of the part. So we need to control the spatial inhomogeneity of the mechanical properties. There are many common defects in additively manufactured parts. So let's say lack of fusion voids. So as you know that in additive manufacturing, we make parts by depositing layers. So there has to be a very good bonding between two consecutive layers. If that does not happen, there is a void between two layers. And you do not want to have your part looking like Swiss cheese. That's very bad for mechanical properties. Surface roughness is another concern. Now, surface roughness can be improved by post-process machining or grinding. But we use additive manufacturing for making very intricate parts having internal cooling channels, so on and so forth. Now, how you can improve the surface roughness of internal cooling channels by using machining? It not only adds cost, but it's sometimes impossible to achieve. So we need to somehow have some strategy to control structure, properties, and defects. And there is no other route except using machine learning. Why? Let me give you two examples. Let's say we are interested in studying some defect, and it depends on variables that you can control during experiment or material properties. So common variables that you can control during experiment: power, speed, laser beam radius, layer thickness, so on and so forth. So there are 12 variables. Now, if you use a simple two-factor design of experiment, the minimum number of experiments that you need to fully explore the effect of all variables is 2 to the power 12, which is 4096. Now imagine, even if you do one successful experiment a day, a PhD student cannot graduate in 10 years. So that's not a viable route. In addition, you see, if I take two prominent variables, power and speed, they vary a lot depending on which additive manufacturing process we use. Please note the logarithmic scale. You can see that the scanning speed in powder bed is 2 order of magnitude higher than that are used in DED. So in other words, we need to explore a wide range of process parameters, which is impossible to explore by experimental trial and error. So that's why we need machine learning that can reduce the parameter space to explore, minimize trial and error, and improve the quality. So in one go, we can understand what we should do to achieve the best part. So there are basically two types of problems in additive manufacturing that we generally solve using machine learning. Regression problems where we have a variable that has continuous values. Let's say molten pool width that changes, that has a particular value. It's a variable. So we can train machine learning algorithm using values obtained from experiments and then use that trained machine learning algorithm to predict, let's say, molten pool width for new experimental conditions. So the advantage is you do not need to do a new experiment. You can use the machine learning, and before doing the experiment, you can know what works and what does not work. So several examples of this type of problem is definitely control of geometry like width, depth, so on and so forth. Grain size, because it's also a variable, it has number, it has values. Residual stress, which significantly varies in the part, and distortion. All of these have some value. That's why they are classified as a regression problem. To solve this kind of problems, generally we use linear regression, neural network, Bayesian network. These are the commonly used algorithms. The other type of problem is classification problem, which is kind of yes and no type of problem. Let's say you are interested in knowing whether for your experiment defect will form or not form. So it's kind of type A and type B, class A and class B problem. Other examples may include solidification morphology. I was giving one example of columnar or equiax grains. So it's also two class A columnar grains, class B equiax grains. So these are the common examples of classification problems in additive manufacturing. Which algorithm we use? Decision tree, random forest, support vector machines, and there are many other commonly used algorithms for classification problems. So now let me give you some examples of both regression problems as well as classification problems. Control of grain size. Since grain size is a variable that has continuous values, it's a regression problem. What we do? We simulate using a grain growth model to calculate the grain size and its distribution in 3D. Now imagine from this 3D distribution you can extract the values in 2D. And now if you take one particular line, you can get the grain size variation along that line. So you can take in longitudinal direction as well as in transverse direction or any other direction you want. So you get a distribution of grain size, uh, number of grains, how many grains you have for a particular grain size. Let's say your grain size is 10 micron, how many grains you have in the longitudinal as well as in transverse direction. So these are pure data. That is a continuous variable. You extract this data and train a neural network, let's say. Then you can use that neural network in future to predict the grain size and its distribution in 3D for new set of experiments. So once you can do that, you can have the idea that how you can control the variables like laser power, scanning speed, so on and so forth to get a grain size distribution that is desirable for achieving a good mechanical property. Residual stress is another problem that can be solved using machine learning, or at least you can minimize the residual stress in additively manufactured part. So once again, you can calculate residual stress in 3D for part using commercial packages or any type of thermomechanical model. So what they do, they take the temperature distribution in 3D and along with the geometry, mass and temperature field, they calculate the residual stress and distortion. And there are commercial packages like Abacus or ANSYS, they can very easily do those. So if we know the values of residual stresses, we can take them and train machine learning and eventually use the trained machine learning to estimate residual stresses. Now, what is the benefit? The benefit is these thermomechanical models to calculate residual stresses are computationally expensive. They take a lot of time. But in contrast, if we have a machine learning algorithm trained using residual stress values, in a very short time, we can calculate residual stresses for different processing conditions, different alloys, so on and so forth. But to train machine learning using those computed values of residual stresses, we need to know how good the calculations are. I'm giving here one example. So residual stress is a vector. It has three major components. I am taking here the through thickness component, the component along the vertical direction. So here is the substrate on which a thin wall is deposited. So two paths, A and B, C and D. A and B is at the deposit substrate interface, and C and D is along the vertical direction. We use hole drilling method, a very commonly used method for measuring residual stress, and measure residual stress along these two lines. Using the same condition, if we calculate the residual stress using a thermomechanical model, we can see that the computed result agree reasonably well with the experiments. It gives us the confidence that yes, these values are correct. We can now use these values to train machine learning. And you can do that for different processes and for different materials. For example, if you fix a material stainless steel 316, you can see that residual stresses vary significantly depending on which process you are using. For powder bed, since we deposit very thin layers, like in the range of 20 to 50 microns, thinner than human hair often, they shrink very less during the cooling and solidification process. They accumulate very less residual stress. In contrast, in DD gas metal arc, we can deposit a lot of material to enhance productivity. That shrinks more during the cooling and solidification and accumulates higher residual stress. Now, if we have a same process, let's say laser directed energy deposition, and compare two materials, titanium alloy and a nickel alloy. Since the titanium alloy has higher yield strength, it can accumulate higher residual stress compared to the nickel alloy. So in other words, this type of well-tested, rigorous models can give you accurate residual stress values for different processes and materials that you can use eventually to train machine learning. For example, let's say we use neural network or random forest. We calculate residual stresses for multiple processing conditions for different commonly used alloys, use the computed value and train neural network or random forest. And then do new set of experiment for which you use the trained neural network or random forest. You do not need to go back to the model again. You use the trained machine learning and predict residual stresses before doing the experiment. And when you do the experiment, you predict the values after doing the experiments. You see that what the model is saying and what you are getting from machine learning are matching very well. And you are getting this kind of accurate result in a significantly less time compared to the model. There is another benefit. This kind of machine learning analysis can tell you that which variables are the most important and which variables are least important, so that we can have some rough idea that which variables we need to control to reduce residual stresses. For example, here machine learning is telling us that temperature gradient, which is the difference between solidus and preheat temperature, is the most important variables. Now, in the welding literature, we know it's a common practice in the industry that People use preheating for reducing residual stresses. So what they actually do, that if they increase the preheat temperature, that means they are eventually reducing this temperature gradient to control residual stresses. So this kind of machine learning analysis can give you some very important and insightful scientific understanding that you can use in practice and solve larger manufacturing problems. Lack of fusion is a very important problem in additive manufacturing. Now here our objective is to find out whether these lack of fusion defects occur or not. So it's eventually a classification problem. So, lack of fusion makes the part looking like Swiss cheese. It has a very poor property. For example, when the void size increases, you can see that the strength, tensile strength, decreases significantly. So, how this kind of voids originate? Let's say this is a molten pool, and I show you the inside structure of the molten pool by taking a isometric 3D cut views. Now, please look at this transverse section. If I jack it up, you can see this is the transverse section of the deposit during powder bed fusion. It looks like half of a watermelon. Now in additive manufacturing, we make a part by depositing many such cracks. So if we combine all of them, many of them, you can see there may be white region in between. And these white unmelted regions are the source of lack of fusion parts. How to reduce them? You may say that, okay, bring these two watermelon closer and you can reduce that. You are absolutely right. This distance we call head spacing. So if we reduce head spacing, the void fraction significantly reduced. So how we can use them in machine learning to reduce lack of fusion? Apart from the head spacing, there are many other important variables that control lack of fusion. So let's say there are head spacing, there are pool depth, Marangoni number that controls the deposit shape, Fourier number that controls the heat transfer rate during the process, and definitely some indicator of temperature is important. So you have the process variables, and the experimental information, whether defect forms or not form. You take those information, you calculate the important variables using a model, and take all of them in machine learning. And obviously, it should be guided by our intelligence or previous knowledge, the rich knowledge base that we obtain from metallurgy, material science, casting, and welding. We take them, develop a machine learning framework which we can eventually use to predict for new sets of experiments whether defect will form or not. So when we go to the shop floor, do the experiment, we can actually reduce the lack of fusion defect. So we will not waste material, we will not waste time and money. Like residual stress, this kind of analysis can also tell us which variables are important and which are less important. So dimensionless head spacing, which is the ratio of head spacing and pool width, is found to be the most important variable, followed by dimensionless pool depth, which is a ratio of pool depth and layer thickness. So essentially, engineers can know from this analysis that if you have a particular set of heat input, so you cannot change the pool width and pool depth, change head spacing and layer thickness to control lack of fusion. Now, if your machine does not allow to change head spacing and layer thickness a lot, then you adjust your power and scanning speed to get proper pool width and pool depth so that you can avoid lack of fusion defect. So in other words, this kind of analysis can guide engineer to control variables for reducing many important defects and improve the quality of additively manufactured part. So if you take the most important variables, the ratio of pool width and head spacing. So this is the transverse section of pool. This is the width of the pool in the transverse direction, and center to center distance between two neighboring pool is called head spacing. The ratio of these two variables, which is the most important variable as machine learning is telling us, if we take that variable and calculate the value of variable for several experiments for many commonly used materials, you can see that this variable has the capability to delineate the experimental results. Above a certain value, you see all blue data point are for no defects, but if you go below that variable, below that threshold, you can see all of the experiments are causing defects. So you need to perform an experiment so that the value of this variable in this blue region, so that you will not form any lack of fusion. How to do that? You combine all these important variables that we were explaining, like hash spacing, pool depth, Marangoni number, temperature, Fourier's number, and use machine learning to get a formula. And we call it as a lack of fusion index. So the lack of fusion index vary between 0 and 1 with a threshold at 0.5. So if this is above zero point 0.5, you will get defect. If this is below zero point 0.5, there is no defect. So you adjust your process variables, select a proper alloy so that the lack of fusion index comes in this region, a very small lack of fusion index, so that we can avoid the defect. Similarly, solidification cracking is another major problem in additive manufacturing. Cracking significantly degrades the mechanical properties and often leads to part rejection. So similar to lack of fusion defect, there are many important variables that control solidification cracking. For example, stress. If we have high stress, it can originate cracks. Ratio of vulnerable and relaxation times, this time ratio gives us some idea that how the material solidifies. Temperature gradient to solidification growth rate tells us whether it will form columnar grains or equiax grains. And of course, the rate at which the liquid metal solidifies and cools. So if we know all these variables, values of all these variables, we can train machine learning to get another index called cracking susceptibility index. So similar to lack of fusion susceptibility index, crack susceptibility index also varies between 0 and 1. If this is more than zero point 0.5 above this threshold, you will observe the crack. If this is below zero point 0.5, the threshold value, you will not observe crack. So in other words, you can fix the processing condition using the experiment so that you will be in the safe region and your parts will not have any crack. Also, this kind of analysis can tell us that solidification stress among these four variables, solidification stress is the most important variable. So how to reduce stress? Maybe you do preheating to reduce the temperature gradient and the stress to reduce cracking. So in additive manufacturing, many things are interdependent. Like the evolution of stress is also connected to the formation of cracking. So if we can reduce one thing, we can also probably solve other things. Like if we can reduce stress, we can also eliminate crack formation. And machine learning is one of the best possible routes that exist today, can help us to do so. How we can perform machine learning calculation in additive manufacturing. So we published last year a review in Nature Reviews Materials where we have identified several open source codes that you can use to apply machine learning to solve major problems in additive manufacturing. So There's an open source user interface based code called Weka. There's a university in New Zealand. They developed this program and made it publicly available without any cost. Scikit-learn, many of you may know, it's a Python-based or C++-based program for machine learning, and there are many other like TensorFlow, Keras, Theano, so on and so forth. And these open source machine learning programs have been extensively used to solve many problems in additive manufacturing. For example, fault diagnosis, porosity reduction, improving dimensional accuracy, controlling grain structure, so on and so forth. There are many such examples. So today we will try to use Weka, the first one, and I'm going to show you how you can use Weka to solve some problems in additive manufacturing. So let me first introduce you how you can download and install Weka in your computer. Whether this is Windows, Mac or Linux, they have executables for all the operating systems. You just need to go to this website. You can just Google Weka. You can also get this website, and if you open this website you can see this screen, and under software you can see download. You can download the executable file, and this is free, and you can install it and run Weka for performing machine learning calculations. So Weka takes data file. As you know that machine learning is all about data, right? So how we need to give data to Weka, we generally use .csv file. So you put the data in MS Excel and save the MS Excel sheet as .csv extension. And you can easily import .csv into Weka and perform machine learning calculation. Now I was mentioning that there are two types of problems: regression problem and classification problem. So the data sheet should look a little different depending on which problem we are solving. So this CSV file or MS Excel file, row 1 should contain the name of the variable. So for regression problem, let's say we are controlling pool width depending on power and speed. So input variables are power and speed and output is width. So the name of the variable should be in the first row. For classification problem, let's say we are controlling defect, we have the inputs and this is the output, defect. Once again, the name of the variables will be in the first row in the Excel sheet. Now for regression problem, since this is a continuous variable problem, we put the values of the variable. But in the classification problem, you say yes or no. You can also select class A or class B. Class A for defect, class B for no defect. It depends on you, but you have to put some character, not the variable. Now we are going to solve two problems, one regression problem, one classification problem. So our problem one is prediction of deposit geometry. Now deposit geometry is a continuous variable. It has values. So it falls under regression problem category. We have a table containing all the data that we will use to train the machine learning. We have three variables: power, speed, and heat source spot diameter. Let's say laser we are using as a heat source, laser spot diameter. And for different combination of power, scanning speed, and spot diameter, we have pool width. So the problem here is we need to train a neural network using these values for predicting molten pool width for different combination of power, scanning speed, and spot diameter, so that we can use eventually the trained neural network in future for predicting pool width for new set of processing conditions. So now let me go to Weka and show you how we can actually use this dataset to predict deposit geometry. So if you download and install Weka and run Weka, you will see this screen. We need to go to Explorer. So before I go to Explorer, let me make sure whether you can see my screen showing Weka. Can you please confirm?
Yes, sir. Yes,
Yes,
sir.
sir.
Great,
Yes, sir. Yeah.
great, great. Thank you.
Thank you, sir.
So if you open Weka, this is the screen you will see. Go to Explorer and you will see another screen that will pop up that has many features for doing the machine learning calculations. Remember, we have saved our data file as .csv. Now we need to import that file here. So we select open file, go to the folder and select CSV from here, and this is the file that I have stored before. See, we have the variable power, speed and spot diameter. These are the input. And the number fourth variable is the output, which is spool width. So we need to take all four of them. We have imported the data file. We have selected the input and output files. Now the next task is to do the calculation. What we need to do? We need to go to classify. And under classify, you can see there are many options for selecting different type of machine learning algorithms. Now, under function, you can see there are many options also. I was describing linear regression as one of the major regression-based machine learning algorithms. So in Weka, neural network is called as multi-layer perceptron. So we need to select this. You can see if you click on this multi-layer perceptron, you have many options that you can play with, like learning rate, momentum, batch size, the number of decimal points that will represent the accuracy, then whether you are using other data set for testing and validation, training time, so on and so forth. So once you start using Weka for solving your problem, you can probably play with all these variables to improve the accuracy. In this case, we are using the entire training set for training the machine learning algorithm. Now you can use cross validation. That means you are dividing your entire training data set into small fragments, and then let's say you are dividing the training data set into five subsets. You say I will use 4 for training, 1 for testing, or 3 for training, 1, 2 for testing. You can do so. Or you can say that I am splitting them in percentage. Let's say 66% for training and remaining 34% for testing, or 70% for training, remaining 30% for testing. You have all the options. So for now, let's use the entire 100% training dataset for training neural network. Under more option, you can see there are many important informations you can use, and also you have the option to write down the final prediction. How you can write down? You can store as a CSV file, you can write HTML. So for now, let's store it in plain text so that we can see the values in this screen. Select OK. Now we are all ready. We have the data file imported, we have selected the variables, we have selected our algorithms, which is neural network represented by multi-layer perceptron. We have the entire training dataset for training the neural network. Now just click start, and you can see we got all the information, and it also writes the predicted values. These actual values, zero point 0.6, 0.63, these are the width value that we provided. And this predicted value is predicted by trained neural network. They are very close. And if you see the error is very less. This is the absolute error. Now, if we plot actual and predicted, and let me show you how they look like. They look like this. So actual pool width that you supply while training the neural network, and predicted pool width that is calculated by the neural network after it is trained. You see that they fall almost on a 45-degree diagonal line. So 45-degree diagonal line means y equal to x. Predicted pool width equal to actual pool width. So if our data falls exactly on this 45-degree line, that means our prediction is 100% accurate. So this prediction is almost accurate, but you can actually play with different parameters in neural network, as I was showing, to improve the accuracy. So let's recap what we have done. So we go to open file, import the .csv file that you have saved in your computer by doing save as option in the MS Excel, and import that CSV file here, select the variables, and then go to classify, go to function, and under function select multilayer perceptron. That's how they call neural network in this program. Once you select multilayer perceptron, you have the freedom to change any of these variables. You can just keep it as is, use the default values, select training dataset, or you have the flexibility to select any other options as you want. Then hit start, and the calculation will be done even before you can blink your eyes. And at the end, you can get all the essential informations that you need, that the predicted pool width. So once you have the neural network trained, you can have a new set of data for which you want to calculate molten pool width. You feed that as a test data set. So you can actually import test data set using this set option and calculate the molten pool width before doing the experiment to see what is the rough values of pool width, so that you can go back to the shop floor and do the experiment and get the desired geometry. So problem number 2, it's a classification problem. Occurrence of lack of fusion defect. We are interested in seeing whether lack of fusion defect originates or not. So as I was explaining, lack of fusion defects originate from improper fusional bonding among tracks. So in powder bed fusion, if you fix layer thickness and head spacing, the fusion bonding among the tracks affected by two variables, pool width and pool depth. So we need to have data on pool width and pool depth. So for different pool width and pool depth, either we do not see defect, no defect represented by N, or we form defect, yes, represented by Y. So our task here is to use this data set, that means data on occurrence of lack of fusion defect at different combinations of pool depth and pool width, train a machine learning algorithms, a suitable machine learning algorithm that can be used to obtain a quantitative tool for future prediction of lack of fusion defect depending on different combination of molten pool dimensions. So we need to have a quantitative tool that we develop now and we can use even after 1 year with very high confidence. Now let me go back to Weka again and show you how we do so. So let me close this window and go back to Weka Explorer again. And when you open the Explorer, you can see the same screen. Now we need to import the data file. So we go to our computer, select CSV file as the data file, and open this. So we are going to use a classification based machine learning algorithm that is called support vector machine popularly known as SVM, for solving this problem. So as we import the data, you can see two input variables, pool depth and pool width, and the output variables, which is the third variable, is defect. So if I select these two input variables and the output variables, you can see that in the dataset we have 40 no, that means 40 cases where defects were not found, and 40 cases for which a defect was found. And Weka also gives you a visual representation of the data distribution. Two classes represented by blue and red, 40 for one class, 40 for other class. Now, how you can use this dataset to train support vector machine and get a quantitative tool for future prediction. Once again, go to classify and select algorithm under function. Now, under function, there is a function called SMO that we use for support vector machines. Now, similar to neural network, there are many functions that you can change. For example, let's take the calibrator, not the logistic function, but sorry for that. Okay, I got the window back. So instead of using logistic, let's take SMO. We are not interested in normalizing the data. We will use the data as is. So select no normalization and standardization. There are many kernels you can select from these options. There are polynomial kernel, normalized polynomial kernel, pre-computed kernel, RBF kernel, so on and so forth. So we select polynomial kernel. You can also use RBF kernels and other kernels. Your result will be little different, but it would be very interesting to see how much they are different. So I have selected. Once again, I am using the entire training set to train the support vector machine, but you have the flexibility to select other options. I am also interested in to write the output as a plain text in this window. So I am all done. I have selected the input variable, selected the data, selected the proper algorithm, the data set. Now I am all ready to run the calculation. And if I hit start, before we can blink our eyes, calculations are done. And look at that. For all 80 data points, it had correctly classified whether defect formed or not formed. So our training is 100% accurate. You can also see that from here. So we had 40 plus 40, total 80 cases. For all 80 cases, it has written the output. So actual output, actual input for defect, no or yes, and this is the predicted by machine learning. So for no cases, it has correctly predicted no error, no defects. For yes, represented by y, where defect formed, our machine learning is also told us that yes, defect will form. So error prediction 1 means it has correctly identified. And you can see that for all 80 cases, it has correctly predicted the data. So that's why this is 100% accurate. And the time it takes is just 0.07 seconds. It's very fast. It's very well tested algorithms that they have put together in an open source form. Another thing is very interesting. I was talking about developing a quantitative tool, right? So it gives you an equation. Some coefficient times pool depth plus some coefficient times pool width plus some constant. What is the significance of this equation? I will just come back in a minute. Before that, let me go back to the PPT and recap what we have done for solving these problems. So we selected open file and then imported the CSV that contained the data of depth, width, and defect. We select the variable and correctly identified that there are 40 data in no category and 40 data in yes category, and it will also show you in visual form. Next step, go to classify, go to function and select SMO from there for doing support vector machine calculation. And once you select support vector machine, you change the calibrator as SMO, which is for support vector machine. We do not need to do any normalization or standardization because we are using the data as they are. Select polynomial kernel. You can also select any other kernel. And next step, you use entire training set, hit start, and you get 100% accurate result. Now, let's go back to the equation. Coefficient times depth, another coefficient times width plus some constant. What are the significance of this equation? And this equation actually help us to develop a quantitative tool. How? This equation gives us the equation of a hyperplane, Z represented by Z. So if you use this equation for different pool width and pool depth, this equation can give you an equation of a plane, this plane. Now this plane is called hyperplane. Now at z equals to 0, this plane cuts the z equals to 0 plane along this line. So if we take a top view, you can see this. So it intersects the pool width axis, the y-axis at 900, almost 900 here. And it intersects with x-axis, pool depth axis, almost like 500 here. So it's orthogonal projection of this plane. So if the data is in this region, it falls under one category. If the data is in this region, the other side of the plane, it falls under the second category. So it correctly tells us that it gives a line that separates this data, no defect, defect data in this region, which falls in this region, and the class B, no defect data, which is in this region, above the threshold, the data will fall in this region. Now for this case, the hyperplane is a plane. It's not a complex curves or complex curvilinear plane. For curvilinear planes, this equation would have been much more complex. But I have selected one example to explain the simplest case where the hyperplane is just a flat plane. So the advantage is, for new set of experiments, you put depth and width and see whether you are getting the value of z positive or negative. If you are getting negative value, that means in this region you will form no defect. If your value is positive, in this region you will form defect. So in other words, it is giving you a quantitative tool that you can use in future for predicting whether defect will form or not form. So we have solved one regression problem using neural network and another classification problem using support vector machine. Now I turn the table to you. I am giving you a practice problems. As you know that hardness is a very important mechanical property. We often measure hardness in Vickers scale, VHM. For additive manufacturing part for different aluminum alloy, Vickers hardness change significantly based on the composition. So as you know that in aluminum alloy we use magnesium, zinc, silicon, manganese, titanium to change their chemical composition in such a way so that we can get a very good mechanical properties. So I have listed here for several different aluminum alloys the chemical composition and corresponding average Vickers hardness values. The problem that I am giving to you is use a linear regression to find out a formula to represent Vickers hardness as a function of chemical composition. How would you do that? Linear regression can be done very easily in MS Excel. So what you need to do, you need to use this dataset and find out an expression where you represent Vickers hardness as a function of all of them. So when you do that, you will get this equation. I am giving the answer so that you can use that to check whether the answer that you are getting during your calculation is correct. So you can see that Vickers hardness is represented by the chemical composition in weight percent for several elements. There are many important considerations before we can use machine learning for additive manufacturing as well as for any other problems. We need to understand the data. As you have correctly pointed out that, since the composition is changing a lot, how we should take the data. Should we take the normalized values or we take the non-normalized values? That's a very important point. We need to, before using it in machine learning, we need to carefully evaluate the data. As you have correctly pointed out, we need to find out the correlation coefficients and to make sure whatever we are using is correct. We do not have any contradictory trends. Selection of variables. Many variables may be correlated among each other. So as you have correctly pointed out that finding out the correlation coefficient can tell us that instead of taking both the variables which are highly correlated, which one we need to select. Selection of algorithms. So we cannot select probably a neural network for solving a classification problems or using a decision tree for a regression problems. So we need to have some basic understanding of selecting a proper algorithms for solving our problems. And fourth, which I think the most important task, interpreting the result. Because sometimes you can see that you are getting two highly correlated variables that are giving high value of correlation, but they are actually not correlated. Like, um, let's say you are getting a correlation between um, laser power and some variable that is not, some output variable that is not correlated with laser power. You should not take those variables. Or you can see some variables that are giving you a wrong representation of relation, which you should also ignore. So we need to have the basic scientific understanding of interpreting the results to figure out what works and what does not work. So one of my fellow colleagues from statistics department used a machine learning algorithm to figure out that what are the most important variables for causing childhood obesity. So he had a lot of data coming from different hospitals in the US, and he figured out that if the pregnant mother smokes cigarette, that will help to reduce the obesity of the child. It's totally false. This is not correlated. So then my colleague has the fundamental understanding that okay, this is not true. We need to change our model. So in other words, we need to have the scientific understanding of the problem so that we can correctly interpret the result and accordingly change the algorithm we are using or change how we are developing the models. So these are the important considerations we need to use before you use machine learning. Um, Machine learning is definitely useful for controlling microstructure properties and defect formation, and I have given several examples for that. And also, as I have pointed out, that there are several well-tested algorithms and open source codes that anyone can use for applying machine learning to solve problems in additive manufacturing. And also, as we are discussing, and there were questions, we need to understand what we are doing. There are several important considerations that we as users need to practice for successful implementation of machine learning. And at the end, if we can successfully implement machine learning, it can reduce the large process parameter space that we need to explore during additive manufacturing, minimize time consuming trial and error, and improve the quality. Now, where we can go from this machine learning? There are other digital tools like mechanistic models, statistical models, control models, also analysis of big data, and also the sensing and control data that are very important. Like you were asking that how we can figure out whether this is a cracking or this is a lack of fusion. During the experiment using high-speed camera, we are now able to capture images, and that image are very important information that we can process as data. So if we combine all these essential things like different types of models, machine learning, big data analysis, data that we obtain during the experiment or by post processing, combine everything under one umbrella and construct a digital twin or digital replica of additive manufacturing process. So in the US and in many other countries, people are trying to develop a digital twin for additive manufacturing, where machine learning is an important building block. So since we are today talking about machine learning, this is a very important consideration that where the future would be maybe after 5-10 years. And currently, not for additive manufacturing, but for solving other problems, many big companies are using digital twins, including Siemens, General Electric, so on and so forth. So for machine learning or deep learning calculations, we need to do computationally expensive calculations, and quantum computing can help us in doing so. So already IBM is telling that quantum computing is able to disrupt and redefine the manufacturing engineering, including additive manufacturing. So what they are doing, they are allowing people to freely access 5 quantum bit quantum computing facility. So if you Google IBM Scikit, you can get to the website and register freely and get the 5 quantum bit computing facility for your problem. SBIR, Small Business Innovation Research in the US, that fund innovative startups in manufacturing and any other domain, they are also encouraging to use quantum computing in 3D printing. So in other words, quantum computing is going to be one of the futuristic options to use in additive manufacturing. So what is the large scale impact of what we are doing? Using machine learning, we are actually discovering a new path for cost effective and rapid manufacturing by reducing time consuming and expensive trial and error test, and by printing many more materials that we cannot print today. Use of machine learning will give us the opportunity to improve the printability of those materials and make more materials available for additive manufacturing to print high quality part. And most importantly, we are all researchers, right? So we need to figure out that how we can create a research environment for everyone. And this soft computing, modeling, use of digital tools, machine learning can give us that opportunity. So we do not need to access a very highly sophisticated experimental facilities always to do great research. So what we need, a computer and a stable internet connection. And anyone can participate in this research using digital tools. So it will promote more inclusive environment where anyone and everyone can contribute. So that's all I had from my side.